Okay, so coming to the last lecture of this series on logic and quantum information. So we've already seen that, well, our main focus has been on probabilistic models, those arising from quantum mechanics and those, as it were, around it, relating to the non-contextual models and then these no signaling models. But we've also seen that a lot of information, a surprising amount of information about the probabilistic behavior can be gained by looking just at the supports, just at the possibilistic information from the model, as we might say, where we just distinguish between probability zero, impossible, and positive probability, namely possible. And I want to take that a bit further and also put it in a more general context. So I want to start by taking the notion of distributions and giving it a useful and quite simple generalization as a more general setting for this interplay between probabilistic and possibilistic notions. And as I said at the beginning, I'm sort of cutting out all the measure theory issues by restricting to discrete probabilities, probability distributions of finite support. Actually, most of the sets we've been considering have been finite anyway. In this case, and that makes it very simple to make this generalization. So a probability distribution of finite support can just be viewed as a function into the non-negative reals, which is non-zero only on a finite number of arguments, and which normalizes. And the fact that it normalizes then guarantees that the range lies in the unit interval. And then the probability of an event is easily defined from this just by summing over the values assigned to the elements. Okay, now what we can do in a very straightforward way is to say that we're using the non-negative reals as the range of our functions, and we could replace this by an arbitrary commutative semi-ring which has sufficient algebraic structure for all the operations we need to set up the basic notions of probability theory still to make sense. And I think Val will probably be using semi-rings in his...
Thank you. I can skip a slide.
There we are. We aim to serve. So it's a very useful notion that occurs obviously in many places in computer science, but so it's just it's like a ring, but where the additive structure is only assumed to be a monoid, and where it will be a commutative monoid, and we'll be interested in the case where the multiplication is commutative as well. And the key thing is that they have this distributive law. So the non-negative reals, that's why I use them rather than the unit interval, because we have normalization anyway. So it's algebraically convenient to say that the structure we're working in is the non-negative reals. And that's a semi-ring, not a ring. And the distributions we get on that are exactly the discrete probability distributions. But on the other hand, we could put in any distributive lattice, and in particular the Booleans, as the semi-ring, and with disjunction and conjunction playing the roles of addition and multiplication. So if I put the Booleans in, what does the notion of distribution mean? Small exercise just to check that we're all awake, at least at the beginning of the lecture. So what is a distribution in the case of the Booleans as the semi-ring, bearing in mind that this is our definition of a distribution?
It's a set.
Sorry?
A set.
A set, but can you be more specific? Sorry? A non-empty set is true, and even more than that. Finite support, so a finite, sorry, did you say finite? No, finite non-empty set. Finite support and the normalization condition, so finite non-empty. Of course, as I say, mostly we'll be applying this to finite sets anyway, but the exact rendition in the Boolean case of what a distribution is a finite non-empty set. And you see, so there's which brings, of course, a lot of examples familiar from computer science into play, and we'll be shortly looking at a salient example of that. And there are lots of other possibilities. We could sort of have a kind of bag semantic, somewhat analogous to what Foucault was talking about in the previous lecture, by taking the natural numbers as the semi-ring. In fact, if we took the reals, a ring and therefore a semi-ring, that would give us exactly signed measures of the kind that we saw came up naturally. We were in the set where we were thinking, as it were, of negative probabilities. So all of these are interesting examples in our context. Now, I've decategorified my lecture, but I am going to mention the word functor here. So we can, given a set, you can define the set of all R distributions parameterized by this choice of semi-ring R. R distributions are finite support, and it's a functor in exactly the same way that the probability case is. And actually, if you define it exactly the way that you see, the functorial action is just this fundamental operation of pushing a measure forward along a map. And even though probabilists don't usually speak of functors, they're always using this push forward action of functions on measures, measurable functions in general, of course, on measures. And statisticians use it too. When you talk about the distribution of a random variable is really a measurable function defined from a measure space into a measurable space, and the distribution of the variable is the push forward of the measure on its domain, which you can therefore avoid mentioning ever afterwards, to the codomain, which is usually the reals. So, and one can then check that this action on maps is actually functorial, which again is used all the time, whether one acknowledges it or not. Okay, so I've made my homage to category theory here, I think. So I mentioned functor. Now, we have this general notion of distribution. And now, in the Boolean case, as we just said, Boolean distributions, two-element Boolean algebra as the semi-ring. They just give us subsets. And in the Boolean, and the point is, we can run all the notions that we've had till now in this more general case of R-valued distributions. And in the Boolean case, this gives us a notion of possibilistic contextuality, where we've replaced probabilities by Boolean values. And the crucial difference, of course, is that you have disjunction as the addition and idempotent operations. So you're losing all counting information. Now, there's a homomorphism, in fact, a unique homomorphism. Units have to be preserved of semi-rings from the non-negative reals to the Booleans. It's the only one there is, which sends positive probabilities to 1 and 0 to 0. And where you get once you've got distributions over a semi-ring, if you have a homomorphism of semi-rings, you can translate distributions across this. And this will say, exactly in this case, send a probability distribution to its support. And this, in turn, will send probabilistic empirical models to possibilistic empirical models. So this is the sort of general context in which that arises in that fashion. By the way, it's a nice little exercise to check that there's no homomorphism from the reals as a semi-ring to the Booleans. And that sort of, well, we'll see why that sort of relates to that fact we mentioned the other day about having hidden variables at the cost of having sign measures or negative probabilities. But in this case, where we're going from the non-negative reals to the Booleans, the induced map on distributions is what we call the possibilistic collapse. And it lifts to empirical models. So given a measurement scenario and a semi-ring, we have the notion of a compatible family of distributions. So we've saying that the marginals on the overlaps, on the intersections of the context coincide makes perfectly good sense. So we have a notion of empirical model, and we write a set of empirical models over a scenario and a semi-ring in this fashion. So the case we've basically been studying till now, the probabilistic empirical models are just the case where we take the semi-ring to be the non-negative reals, and the possibilistic models where we take it to be the Booleans. And everything works, all notions relating to contextuality, global sections, and so on, work across this broader variety of situations. Well, there's, so in particular, so I mean, just being slightly, I mean, okay, so now I'm mentioning natural transformation. If you have a homomorphism of semi-rings, it actually, it translates into a natural transformation of the appropriate kind, firstly on these functors, d sub r to d sub s, and then it lifts to, well, basically this is the formal content of what we were saying about it translating an empirical model with R-value distributions to an empirical model with S-value distributions. If you think in terms of the table, we're just translating the probabilities or the R entries in the table from the empirical model over R into S entries along this homomorphism. And if we apply this in the case of this canonical homomorphism here, then it's exactly the possibilistic collapse. And here's a very simple general fact. That if we have a global section for an empirical model over the semi-ring R, and we have this homomorphism, then we can translate it in this way into a global section for the corresponding model over the semi-ring S. So you have the following result. So if you think about by contraposition, to say we're non-contextual is that we have a global section. So what this is saying is that the property of being contextual the property of having a global section is transferred along the homomorphism. So the property of not having a global section will be reflected. In other words, if the image empirical model is contextual, if it has no global section, then the original empirical model must have been contextual. That's just by contraposition. If there had been a global section over E, it would have been translated to a global section over H of E, showing that H of E is non-contextual. So non-contextuality is preserved, contextuality is reflected. In particular, if the possibilistic... So another way of saying that is, I mean, and let's just think of it with probabilities and possibilities, it's easier to have a global section possibilistically than it is probabilistically. It's easier to have a witness for non-contextuality, if you like, a hidden variable model, possibilistically than it is probabilistically. So if we don't have one possibilistically, we certainly don't have one probabilistically. The converse, however, is not true. And this was already the first part of our hierarchy of notions, probabilistic contextuality a la Bell, but Bell is not possibilistically contextual, and then probabilistic contextuality a la Hardy, which implies probabilistic contextuality. Sorry, possibilistic contextuality, which implies probabilistic contextuality. And this is a general fact about these things. Okay, so and one can develop more about the hierarchy that we've discussed and other unrelated hierarchies in this context. But instead, what I want to do is to pick up on another point that arises from this, which is that given that we now see that familiar things like Booleans and finite sets just appear naturally in this language once we take the case with the Boolean of an appropriate semi-ring, what happens to our discussion of contextuality? Does it have some more familiar manifestations? And indeed it does, and here's one that's particularly close to home here, since it picks up on one of the themes of the program and a central topic in computer science, namely relational databases. The remarkable thing is that there's an isomorphism, one could, I think it's fair to say, between the basic situation we've been describing, arising from analyzing contextuality in quantum mechanics, and the basic notions and definitions in relational database theory. And very nice discussions with Fokion a few years ago led to the clarification of this. And So here is a table of the kind that we've, of the way that the database tables are usually written, where we have these attribute names and then a set of tuples with a value for each of the attributes. So this we recognize. Something about European cooperation comes to mind here, but I'll pass on. Now, what I want to say is that the tables we've been writing in the possibilistic case, and we're going to relate this to the set semantics of databases, the usual set semantics of databases, but indeed by what we've been saying, by taking other kinds of distributions valued in other semi-rings, we could also relate it to different semantics of databases, bag semantics, or some version of probabilistic databases. But let's just take possibilistic case and the Hardy model again. This can be thought of as a little relational database. The change of perspective is we now think of these variables or measurement settings as the attributes. We think of the outcomes as the data values, and we think of a joint outcome of measuring all the variables in a context as tuples. Then the rows of the database each turn into a table in exactly the usual sense. So each row here turns into a little table with the respective attributes. And you can see, in fact, that specifying what the contexts are is like giving the schema of the database. It's saying what are the set of tables with their respective attributes. So it's actually a perfect correspondence with these notions. So given this, it's irresistible to ask the question, what is the database property corresponding to the presence of non-locality or contextuality in the Hardy table? And the answer is actually a very classic answer, which has already been described by Fauquion in his lectures. In fact, it was even the sort of subject of the universal relation wars, or right. So the question is there a universal relation? Is there a big table, at least up in the sky, as it were, over all the attributes mentioned anywhere in the database, from which we can recover all the tables in the database by projection? That is exactly what the question of the existence of a global section turns into. And this was, of course, well studied and indeed debated, fiercely debated in the database community, I suppose circa late 70s, early 80s. So we could actually make quite a comprehensive dictionary, as we've just said, between these notions. Let me mention this final entry here, which is a beautiful story of its own. There's a beautiful paper by Vorobyev from around 1960. One of the, I guess, maybe the main founder of the in that era, the era of the Soviet school of game theory, and motivated by game theory in 1960, which notice is not only before the database notions but also before Bell's paper. He wrote a paper containing the following result, which, if I put it in our terms, if you have an empirical model over a simplicial complex or a hypergraph scenario, as we've described it, exactly satisfying the compatibility conditions, under what combinatorial conditions on the structure of the hypergraph can we guarantee that any such empirical model will have a global section? And he actually gave combinatorial conditions on the hypergraph, or if you prefer, the abstract simplicial complex, necessary and sufficient conditions to guarantee this. And the conditions are actually equivalent to the condition we know as acyclicity of database schemes. It's exactly those conditions. So it's a beautiful paper, and Ruin, his thesis, has looked at a generalization of this, where you take this over in the setting we've been discussing over a general semi-ring. Okay. And yeah, because, as we've said, because of the this kind of generalization with different semi-rings, we can look at various variants. Okay, so I'll leave it at that. I mean, it would be nice to think that one could build on these connections and have some fruitful results that would come out of this. I mean, one direction where some progress has already been made is the work with Fokion and Georg, which I mentioned briefly in a previous lecture, going into this direction of robust constraint satisfaction. But I'm sure there should be things in relation to databases. So now I want to talk about a topic which brings out this idea that we can gain information about probabilistic structure by looking at possibilistic structure. And in particular, we can come tantalizingly close to a full combinatorial characterization of the no-signaling polytope, which, as we've seen, is a fundamental object of study in contemporary quantum information and foundations, this broader class of theories, which includes the quantum case, but includes things that go beyond as well. And trying to understand the structure of that has been an important theme in the current work in the quantum information area. And we can come rather close to a combinatorial understanding of these polytopes, which are quite complicated high-dimensional objects, in possibilistic terms. But there remains some questions which might well be the kind of things that progress could be made on here in this great environment with so much expertise in many of the relevant areas. So, as we've said, we can fix a measurement scenario, and this will all be generic for any measurement scenario. We get a set of probabilistic empirical models. It's always convex, closed under convex combinations. We can represent the models as points in this high-dimensional space. And since it's defined by a finite number of linear constraints for each fixed measurement scenario, it's going to be a polytope. So remember, we actually wrote down examples of the no-signaling equations, which these things that express that the appropriate marginals coincide, and together with non-negativity, of course. Okay, so what is the structure? So the question is, what is the structure of this polytope? And in particular, we're focusing here on the combinatorial structure of the polytope. And one of us says that so the object that's often used to give the combinatorial structure is the face lattice. The set of faces of the polytope ordered by inclusion. In fact, the combinatorial type of a polytope is defined to be given by the isomorphism type of its face lattice. On the other hand, so this is directly the thing obtained from this polytope of probabilistic models. On the other hand, we have something that's defined apparently quite differently. Namely, we have this possibilistic collapse, which for each probabilistic model takes us to a possibilistic model. Which is just a set of Boolean vectors, and in an obvious way, they can be ordered component-wise. So 0 is less than 1. So we just ordered tables component-wise. And then the result is that actually this face lattice is isomorphic to this lattice of possibilistic models. There's just this slight adjustment in that the face lattice is taken to include the empty face, and so we need to add a bottom point to the, because obviously we have the normalization, so we don't have the empty model. So if we add that one point at the bottom, we get an isomorphism of these lattices. So that's the result with, which is in joint work with Rui, Shane Mansfield, Ray Allen, Kohei Kushida, which I'll describe now. In fact, the result applies to a wider class of polytopes. If you think about the way that the no-signaling polytope is defined, the constraints of the linear equations giving no signaling, this sort of the fact that marginals coincide, and non-negativity. So in geometric terms, it's a polytope that's defined by its affine closure intersected with the non-negative orthant, is it called, the non-negative half space, intersection of half spaces. I forget the terminology. They're just the set of non-negative vectors. Now, we can say that a polytope is in standard form if it is defined in this way. In other words, it's defined by a set of not necessarily homogeneous linear equations together with a non-negativity constraint. It's a standard result in linear programming that every linear program can be put in a standard form where it's given by equations together with non-negativity. So the result is, for any polytope in standard form, there's an isomorphism between the face lattice and the set of supports of the points ordered by inclusions. There's a meaningful general notion of support which generalizes this idea of possibilistic collapse, although it doesn't really have the interpretation of the support of a probability distribution unless we do actually have the case of a specific polytope like the no signaling polytope. Okay, so just to briefly review the usual notions. So we have the idea of polytopes. We have the idea of a face, which is given by, specified by an inequality like this. And then the face is, if we have an inequality valid for the polytope, then a face will be the set of things which actually satisfy the equation. So it sort of cuts the polytope at that point, at that lower dimensional point. And then the set of faces is naturally ordered by inclusion, and this is what's called the face lattice. And in fact, these are well-studied things. They have a lot of structure. They're finite lattices, obviously, for a polytope, and they're atomistic and co-atomistic and graded. So they're very sort of regular and nice lattices. One should note that meets are given directly by intersection of faces, whereas joins have to be defined indirectly. Of course, because it's a finite poset, as soon as you have meets, then you also have all joins, which are defined indirectly as the meet of all the upper bounds. But the definition sort of works, well, you can, not so difficult to define, but it's not the one that's given immediately. This is interesting because of something that will come up later when we look at an isomorph of this lattice. Right, so as we say, this is the face lattice, often called the combinatorial type of the polytope. So it's disregarding metric information, but giving all the information about how the combinatorial object is built up from its lower dimensional components. The important notion of interior for a polytope is the relative interior, which is defined in this fashion because of dimensionality issues. So we have to take here the affine closure of a set in order to get the useful notion of an interior. So a point is, and there's a nice way of characterizing this relative interior, which has a nice intuition behind it. A point is in the relative interior of a polytope if the line segment from any other point to it can be extended beyond it while remaining in this. Actually, this works for more general convex figures than polytopes, but we only need it for polytopes. So a point is in the relative interior if any other point to this given point can be extended beyond this point while still remaining in the set. And there's the notion of a carrier face of a polytope. So there's a standard way of decomposing a polytope as the disjoint union of the relative interiors of its non-empty faces. And that means then that we can define always a map which sends each point of the polytope to its carrier face, the unique face in whose relative interior it lies. This is all, these are all standard notions. So as we said, a polytope in standard form we call something like this, which more concretely means it's defined by equations together with non-negativity. And we can define a support map. So this is the generalization of the possibilistic collapse, which sends a vector in the non-negative space non-negative orthant into just a vector, a 0, 1 vector. And it does the same thing we were doing with the possibilistic collapse. It keeps 0 fixed and sends anything positive to 1. And this naturally has a component-wise ordering, and you can see that there's a natural way of defining the join as a component-wise Boolean disjunction. We can see that if we take the support of a convex combination of points, then they will just be given, I mean, this goes to just this pointwise join. What we see then is that, and since this was a convex set to start off with, we get this closure under joins. And that tells us that this is a finite partial order, which moreover has all joins. Therefore, by the same reasoning as we saw before, it's a finite lattice. But in this case, it's the joins which are described directly, and it's the meets which have to be described indirectly. So a meet will be the join of all the lower bounds. So we just need to add a bottom element here in case the 0 vector wasn't in the polytope we started off with. If the polytope did contain 0, then it would be trivial, in fact. Okay, and then we have a very simple observation, which is that we get this isomorphism that because of the fact, well, it's rather easy to show that I mean, this is what we're basically going to show. It's a very simple observation, but then this will tell us automatically that we have, so we're going to have surjective maps starting from the polytope, either for a vector to its carrier face or for a vector to its support. And once we show that inclusion of carriers is equivalent to this component-wise ordering of the supports, we'll immediately know from this that there's an isomorphism between these two partial orders, between these two lattices. So that's what we do here, and it's actually a simple argument just using this characterization of the relative interior. What we basically do is we show that, in fact, for any standard polytope, the carrier face is just this face given in this concrete fashion. So what we do here is we sort of have the complementary vector, which has 0s wherever the vector we start off with is positive, and 1s wherever the vector we start off with is negative. And this then defines a face which is going to be 0 exactly on those vectors whose support is included in the support of the vector that we started off with. And the main thing is to show that this is indeed in the relative interior of this face, and there's a little argument to do that. So once we know that, then it's very easy, once we've described the carrier face in these terms, to verify this condition. Pretty much directly by construction, we see that the ordering on carriers, just from this, the way the carriers are defined by these the things generated by these complementary vectors, correspond directly to inclusion of supports, and then we get this isomorphism, which was our result. And I mean, so it's a simple result, but it has some nice consequences. Models are in the relative interior of the same face if and only if they have the same support. An empirical model has full support even if and only if it's in the relative interior of the no signaling polytope. So any logically contextual model must lie in a proper face. The vertices of the no signaling polytope are exactly the probability models with minimal support. Moreover, there is only one probability model for each such minimal support. So this is why we said that, for example, we said that the PR box was uniquely determined, the probabilities were uniquely determined from the support by the no signaling conditions, and that is a very special instance of this general fact. So the equations forced, in fact, in that case, all the probabilities to be the same, which meant that we had to have the uniform distribution on each row. But that's actually a completely general fact. So the extremal empirical models, we could say, are exactly those models which are completely and uniquely determined by their supports. And actually what they're going to be are, on the one hand, the deterministic models, which certainly have minimal supports. They're going to have one on each row. Those are the vertices of the non-contextual polytope. And then they're going to be the strongly contextual models with minimal support. And those will generate the rest of the no-signaling polytope. So yeah, that's actually what I'm saying here. So we get, in principle, what looks like a very nice combinatorial description of the no-signaling polytope. There is one snag, though, which is what's going to lead to this open question that I was mentioning. By the way, I may be going a bit fast. I don't know if there are any questions about any of this, but these are, well, I'll ask questions if you have them. So this almost looks like a nice combinatorial description of the no-signaling. Well, it is a nice combinatorial description with lots of nice consequences, but there is one snag. And the snag is that we talked about supports of probabilistic models. So it's not a fully self-contained combinatorial description in terms of the possibilistic models. What we would like is something that only talks about the possibilistic models and which picks out the correct ones to be the vertices of the no-signaling polytope. And so the question broadly is, can we characterize the combinatorial type of the no-signaling polytope using only possibilistic notions? So this is what we've been saying. We get this map that takes us from probabilistic things over the semi-ring of non-negative reals into the possibilistic case. And we want to give an intrinsic characterization of the image of the possibilistic collapse map using only possibilistic notions. So there are, in fact, we sort of already said that there are examples. One thing we could ask, given a possibilistic model, is does it come from a possibilistic no-signaling model? Does it come from a probabilistic no-signaling model? By all the things we're saying about this translation by homomorphism, if you start with a probabilistic no-signaling model and map it down to its possibilistic collapse, that will certainly be no-signaling. It's just a preservation of equations. The question is, what about the converse? And the answer is that, as we might expect, since being no-signaling possibilistically over the Boolean semi-ring is a weaker condition than being no-signaling over the reals, over the non-negative reals, there are in fact quite simple examples of possibilistic empirical models that satisfy no-signaling in the possibilistic sense, but are not the support of any probabilistic empirical model. And here's a fairly simple example of such a thing. If you think about how one would prove this, one would take the no-signaling conditions, and here we're picking out the positive elements with these ones, remember. So we're going to get certain equations that say, for example, that say this is alpha and this is beta. This is probably these comparing this row and this row, we're going to get a no-signaling equation. So here is alpha positive, beta positive, gamma positive. If the sum of alpha plus beta equals gamma, then we know that, for example, gamma must be strictly larger than alpha and beta. So we're going to pick up constraints of the form of strict orderings between different elements. And the point is, in this example, if we look carefully and we write down all the constraints of that kind we get, we end up with a cycle of such strict ordering constraints. So we end up with a conclusion that alpha must be less than alpha, which refutes the possibility that this could have come from any probabilistic model. So, the image is not it's not a surjective map. And all the arguments that we know of are of that form. And it would be nice if there was a sort of logical theory just focusing on this issue of the orderings that can be inferred which would such that one could prove that a possibilistic model given in these terms came from a probabilistic one exactly when this theory told you that it did, where the theory didn't refer at all to the reals or anything outside the possibilistic realm. Okay, so we know that the map is not surjective, but we could ask in the case of the minimal ones, maybe they, where they have sort of fewest number of elements in their support, so that intuitively perhaps they won't generate many of these nasty strict inequality constraints, that maybe they're always realizable as supports. So this seemed promising, but it turned out not to be the case. The moderately complicated counterexample. So here's a concrete scenario. It looks like this. It can be drawn as a bundle diagram of the same kind we were looking at earlier, and with 3 values in general in each fiber. And what we get from the constraints, the no signaling conditions give us a lot of equations, and in the end it tells us that all variables must be equated. Because it's minimal, if we well, it is minimal because if we set any variable to 0, all must be 0. So there can't be any normalized model sitting below it. So but there is a remaining non-trivial equation, which is exactly the one we don't want. A equals A plus A. It works fine in Boolean algebra, but not with positive reals. So therefore, there's no real solution, and this can't come from a probabilistic model. And we can actually convert this into a Bell scenario type example as well, with even fancier picture. So it's still an open question to give an intrinsic characterization of the image of the possibilistic collapse map using only possibilistic notions. I mean, that's not a terribly precise formulation, but I think, you know, it would, as I say, it would be nice to have a logical theory which directly answered that question without bringing in the whole theory of the reals. Okay, so I have 15 minutes or so. So I thought I would say a bit about the Cochin-Specker theorem, which is a famous result in the area. Sam, you were a student of Cochin, is that so? Did you ever discuss the theorem with him?
A little bit, yes.
Yeah. So. Sorry?
I have been a student of Specker.
Well, there we are. So it's fully referenced. Well, I better be careful what I say.
Janus also.
Oh, right. Yes, of course. Yes. Janus Specker very well. Yes. So, right. So it's a classic result of the field, and I just want to show how it can be seen and fitted into the general perspective we've been discussing in these lectures. And again, there's a intriguing open problem, and there are some beautiful combinatorial geometry has been used in the creation of particular Cochin-Specker arguments. So what does the Cochin-Specker theorem do? We've already discussed Bell's theorem and a broad notion of contextuality. The particular point which we get from Cochin-Specker proofs is that they offer state-independent proofs of strong in our language, of strong contextuality in quantum mechanics. Remember, strong contextuality is the strongest form, and it can be expressed purely at the possibilistic level. And the extra thing we get from Cochin-Specker type results is that whereas we've been looking at empirical models which are generated in the quantum realm by a state with measurements, for Cochin-Specker type proofs, you only need to see the combinatorial structure of the measurements, and that already tells you for any possible state that a strongly contextual model will arise. So it has an extra strength in that sense. But there is a sort of trade-off. Actually, Bell, some people refer to the Bell-Cochin-Specker theorem because Bell had another paper which was published, I think, in 1966, although he actually wrote it before his 1963 It's a 1964 paper, I think in 1963, and it spent some time on an editor's desk. But it had a version of with a different proof of a Cauchy-Specker theorem. But Bell was actually wanted to prove the theorem for his 1964 paper because although in a sense it has weaker conclusions, it isn't state independent. As we've seen, you need to have specific states to generate those probabilities, but it also has weaker assumptions. The fact that you have Alice and Bob who are separated, whereas no such separation is generally possible with a Cauchy-Specker proof, and indeed Bell-type scenarios in general do not lead to Cauchy-Specker arguments. So you can have one or the other. But people have been making, I mean, the other thing about the Bell argument is that it led directly to experimental tests, starting with Asper's work in the 1980s, as we mentioned, and culminating recently in these recent celebrated experiments from the end of last year. But people have also been testing, an increasing number of experimental tests of contextuality over the last few years. Okay, so what is the, how can we give a general formulation of what Cauchy-Specker arguments is about? So the shape of the sort of game we're going to, of the setup we're going to describe, we're going to have two valued outcomes. That will be quite sufficient. And we're going to talk about possibilistic models again, because after all, we want to prove strong contextuality, so it is really a notion that lives naturally at the possibilistic level. So, so we just have to give a set of vertices and this hypergraph, this family of sets of compatible variables. And the particular form, again, can be expressed completely independently of the issue of quantum realization. The model, well, we can say that a joint outcome over a context satisfies the Cauchy-Specker property if exactly one of the variables in the context takes the value 1. So it's a sort of coloring constraint. Exactly one of the variables in each maximal context takes the value 1. And we can then define an appropriate possibilistic, a maximal Cauchy-Specker model by setting well, so this is going to be a possibilistic model, so it's a Boolean distribution, but we can just think of it as a set. So it's just the set of all those assignments satisfying the Cauchy-Specker property. So really, therefore, this model is uniquely determined once we've given the hypergraph. All the information is there. And if we regard the elements of X as propositional variables, we can think of this as a truth value assignment. And in fact, the Cauchy-Specker property for an assignment is equivalent to this formula being satisfied, which is just another way of saying that exactly one variable is true. But it could be any one. Okay, and then, yeah. Okay, so a Cauchy-Specker construction in these terms simply then is a Cauchy-Specker model which is strongly contextual. And explicitly in logical terms, that's equivalent to saying that this formula is unsatisfiable. Yeah, and we can generalize it in various ways. We don't have to consider the two-valued case, and then that's kind of like moving from a satisfiability problem to a k-valued constraint satisfaction problem. So here is something we saw earlier. It's a particular and well-known construction. It's one of the simplest that's available. It works in R4. Well, I mean, what that means we'll say in a moment, but it works in R4, not in R3, where the real game is, as it were, that we'll describe shortly. So it's got 18 variables. There's a measurement cover of 9 sets, and you see each of these sets consists of 4 of the variables, and we can ask the question, is this a Cauchy-Specker construction? So this has a well-defined meaning, quite generally now. It's about whether this formula is satisfiable. So can we derive information from the combinatorial structure of this configuration that gives us a quick answer? Obviously, we could enumerate all the... So there is a nice combinatorial condition, and this is a generalization of what's known as the parity condition that's been widely used in, for Koch and Specker. So for each set, for each variable rather, we can define u of x to be all the contexts that x appears in. And what we can say is that, so what we're asking is, just to be, just to sort of get behind this formula, is we're asking for an assignment to all the variables, which then satisfies the property that exactly one of the variables is true in each context. And what you can see, the sort of salient thing one can see here is that there are 9 contexts, and each variable appears in exactly 2 contexts. And that's going to tell us that there can be no such assignment. And here is the more general form of that combinatorial condition. If there is such an assignment, then every common divisor of the set of all these sort of appearance numbers, incidence numbers of all the variables, must divide the cardinality of the hypergraph, the number of contexts that we have. It's perhaps a nice thing to think about. It's not particularly hard to prove. And applying this to the above example, we notice that the cover has 9 elements. Each element of x appears in 2 members, so greatest common divisor is 2, and it doesn't divide 9, so we conclude that this is contextual. There's a nice take on this with cohomology, which I haven't talked about in these lectures, so it fits in nicely with that picture as well. So cohomology detects all of these cases of contextuality. Okay, so this is all purely combinatorial, and as yet we haven't indicated any connection with quantum mechanics. So the other side of the picture is to say, when does one of these contextual Koch and Specker models give rise to a quantum mechanics witness of contextuality? And the idea is this, and this is, well, it's quite, of course, quite related to the things that Simona was talking about, and also goes back to the, well, I mean, some of the main general facts about this kind of thing go back to this work of Lovash. So what we get is a witness when we can label x with unit vectors in Rn for some fixed n, such that the families of sets that we're considering in our cover, in our set of contexts, consist of those subsets which form orthonormal bases. Well, we specifically have to say that those things which are subsets form orthonormal bases, so therefore they're all going to be the same size. And the point of our previous example with the 18 vectors and the 9 contexts, each with 4 elements, is that we can label those 18 elements with vectors in R4 such that the 4 element subsets are indeed orthogonal. So this is one of the most economical known examples of a Koch and Specker construction. An interesting point is that the triangle that we've discussed a couple of occasions, this very simple configuration, which would be a perfect example of a Koch and Specker model. I mean, this is, so if we want only one of the vertices in each, for each edge to have the value 1, then we clearly get an argument for strong contextuality. The problem with realizing this in this way is that the notion of orthogonality we're using is a pairwise notion. So if all the pairs are orthogonal, then the whole set will be compatible. So we don't get a witness from the Specker triangle, which is why Koch and Specker had to come up with a much more elaborate example. But we'll come back to that in a moment. Given such a fact, so we still haven't fully made the connection with observables, the kind of measurements as we've been talking about throughout the week. So how do we do that? And this part is often skipped in presentations, so I think it's useful just to mention this. So given such a family of vectors, we can construct observables corresponding to each compatible family, where the outcomes, if you like, encode the eigenvectors, eigenvalues, I should be saying. This means that for any state, the result of measuring, actually I do mean that, so therefore the point is that encoding will guarantee this Cauchy-Specker property that we were mentioning, that that each outcome that we can get will correspond to coloring exactly one of the vectors in that context, therefore in the orthonormal basis associated with that observable, exactly one of them will be picked out, be colored 1, all the others will be colored 0. So the Cauchy-Specker property is built in, and that's independent of which state we use. It's just a feature of the structure of the measurement itself. And that's why this is going to yield a state-independent argument. So hence we get a state-independent proof of strong contextuality in quantum mechanics wherever we have such a labeling. And there are some conditions given in the case of graphs. There are conditions given by Lovash and co-authors about when suitable colorings would be possible, but it's not a complete characterization. Okay, so now we come to the sort of challenge problem that's that has aroused quite a lot of interest, which is of obtaining Cauchy-Specker constructions. We saw an 18-vector construction in 4 dimensions. Of course, the more dimensions you have, the easier it gets to construct such examples. But the minimum dimension in which such examples can be constructed is 3, and that's where Cauchy and Specker gave their original proof. So there's particular interest in obtaining Cauchy and Specker constructions in R3. So one can prove that you just can't get such a thing in R2. It's an interesting point that Specker actually had a paper in 1960, which really is a beautiful paper, which has been sort of revisited and discussed a lot the last few years. Has a beautiful parable of the seer, for example, which is very nice to read, and this triangle, incidentally. And he sort of, as a throwaway remark, he sort of says, and obviously this sort of situation can be realized in quantum mechanics, but it seems this didn't have too much of an effect. So several years later, Cauchy and Specker came back with their paper, and they really constructed an example with 117 vectors, 39 bases in R3. And there's a famous picture of sort of how these things are inscribed on a sphere. The current record is 31, obtained from a construction by Perez. And there's also ideas by Penrose and the Penrose dodecahedron, I think it is, and some very nice use has been made of combinatorial geometric configurations in order to generate to generate families of rays which will give rise to Cauchy and Specker arguments. So the smallest known number is 31. There was some work a few years ago by Joel Waknin and one of his students, which established a lower bound of 18 with a lot of computation as well as a lot of clever analysis, and that was recently improved to 22 by 2 students at Nijmegen in Bart Jacobs' group. So the current lower bound is 22 and the upper bound is 31. Okay, so
Samson?
Yes.
Since this is a satisfiability question,
Yes.
Have people tried SAT solvers on this problem? Is that what?
Yes, I think that has been used to some extent, but I think often you can, by finding a suitable combinatorial argument, you can kind of shortcut. But there has been a lot of computational exploration there have been particularly a couple of authors, Pavicic and our colleagues who've done quite a lot of computational exploration. I think the work by Joel was more using computational geometry tools, I think. But yes, in principle, one could. But of course, one's exploring, you know, a big space of possible things. Okay, so coming back from that particular topic, just to wrap up this this series of lectures briefly. So I just want to come back. I mean, if our sort of message, particularly in this lecture, has been that we can find similar structures further afield, for example, this connection with databases or constraints. So it's natural to ask the question, why do such similar structures arise in apparently different settings? And I think I'd be prepared to argue, I mean, I think it's not too outlandish to argue that the phenomenon of contextuality is pervasive, and this idea of local consistency, global inconsistency, even a familiar enough phrase, I mean, certainly well known in constraints. And once we start looking for it, we can find it in many places. Of course, what would be good is to have a common mathematical structure and have a sort of a theory with some breadth of application. So we've discussed a lot connections with quantum information foundations, which is the main motivation as far as I'm concerned, but there certainly are these wider things as well. I'll mention a couple of papers just when I finish up. I mean, various papers are available on the archive. As an overview, there was a recent paper in the bulletin of EATCS, also available on the archive, which might be a sort of a good thing to look at. And I just thought I'd show and mention some of the people I've had the pleasure of working with on these things. Adam Brandenberger, with whom I sort of introduced the general setting I've mainly been using as a framework for discussing things in these lectures. Lucian Hardy, we've heard of the Hardy paradox, and he worked with him on logical Bell inequalities. Rui, who's here, Shane will be visiting later. I mentioned the work on robust constraint satisfaction with Fokion and Georg. And Linda's here, Giovanni will be visiting later, both doing their PhDs in related topics. Carmen Constantin, Koei Kishida, and Manoush Sadrazadeh. So, and I'd be delighted if I can add to this list over the course of this program. So here's a few references. So thanks very much for staying with me during the week, and that's it. Thanks.
When we prepared the 90th birthday for Specker, I checked the citation. It was around 300-400, and I checked now for the Cochin, and it's over 2,000.
Yes.
6 years.
Yes, and the interest is, I mean, as I say, people are now doing experiments for testing contextuality, and one of the remarkable things about quantum information is that things that were seen as very foundational have become much closer to things that are seen as, you know, really connected with applications in the field. So absolutely. Incidentally, Anton Zeilinger likes to show a graph of the EPR paper from the mid-1930s, which shows this remarkable exponential growth as well.
Can you say if there is anything related between contextuality and the conventional notion of conserved quantities in physics?
Conserved quantities. Gosh, perhaps you can help me. I'm not sure. It seems to sit in a different, I mean, obviously there are things like energy and so on. I mean, I don't quite see the connection. What does seem to, I mean, so I think, you know, we were discussing yesterday the issue of quantifying contextuality, and I think there are clearly robust measures. And but this is all at somehow at the level of information. And the quantum information, the sort of information revolution in physics is bringing it much closer to perhaps the way of thinking about things that we're familiar with in the sort of logic and computer science community. A lot of physicists are still resistant to that trend, and they think of information as something, as it were, sort of that we project onto the world rather than something fundamentally physical. But I think the ideas may have to change as these developments, quantum technologies and so on, continue. But I don't know of anything precise to say in connection with that. Prakash.
Remark. So conserved quantities are typically associated with symmetries.
Yes.
And probably I don't see really a connection between symmetry and contextuality. Is there such a thing? Wait for the next workshop on symmetry.
We have to wait for the workshop on symmetry, yes. By then, the aim is that... Okay. Any other questions, or shall we break for lunch? Okay, great.